This video is going to discuss the innate immune response. Now, we as humans encounter many harmful pathogens that make us sick, like bacteria. To protect ourselves from these organisms, we have an immune system. Innate immunity is the non-specific first line of defence. But how does this response protect us? There are various mechanisms and barriers that are present. The first being physical barriers such as the skin, mucosal membranes, for example in the lung, or lysozyme. When these physical barriers are breached, we have the second type of barrier, which are immune responses like the cytokines, the complement system, or acute phase proteins. Before we go into detail on the response, let's have a look at the cells that are actually involved. Neutrophils, basophils, macrophages and monocytes, dendritic cells, and eosinophils. These cells originate from hematopoietic stem cells in the bone marrow. From this we get these progenitors. The innate cells that we spoke about come from the common myeloid progenitor because they're leukocytes. The common lymphoid progenitor forms natural killer cells or lymphocytes, which form the adaptive immune response. Here is an anagram in order of abundance, with neutrophils being the most abundant. So let's say a harmful pathogen comes along and breaches a physical barrier, as shown here. We have resident immune cells that are already present in the tissue. We have macrophages and dendritic cells which send signals to recruit additional immune cells into the tissue. But how does it do this? These innate cells include a set of inherited receptors which will interact with the pathogen or its associated patterns. These receptors are called pattern recognition receptors. Receptors recognise patterns associated with pathogens or damage. Once associated, a cascade of signalling events occurs. Essentially, cytokines that promote inflammation are released and transcription factors like NF-kappa B are activated. These factors affect mechanisms that are needed for repair, which include the formation of new blood vessels, cell proliferation and the degradation of the extracellular matrix. Here are some examples of cytokines: interleukin 1, 6 and 12, TNF-alpha and interferon gamma. Interleukin 1 specifically has an important role in elevation of body temperature and activation of macrophages. These cytokines can also promote inflammation. Inflammation is the body's first response. It's beneficial only when acute and recruits extra immune cells. There are 5 fundamental characteristics of inflammation: rubor, which is redness; dolor, which is pain; calor, which is heat; tumour, which is swelling; and loss of function. Inflammation is only beneficial when acute. This means the response eventually dampens down and cytokine production has decreased. When the response doesn't dampen down after getting rid of the pathogen, inflammation becomes harmful, or in other words, chronic. So what are the benefits of acute inflammation? First of all, it isolates and gets rid of the pathogen and stops it from travelling to other tissues or circulation. It also gets it ready for healing, but last but definitely not least, it enables phagocytosis. Phagocytosis consists of 4 steps: attachment, internalization, degradation, and exocytosis. So the harmful substance is internalised to form a phagolysome. Lysosome fuses with this to form a phagolysosome and degrades. Degradation can occur either through antimicrobial peptides or acidification. When an individual's cells are damaged or injured, the same occurs, but instead it associates with danger molecular patterns. With regards to injury, the myeloid cells release constituents called inflammatory mediators, which include histamine and bradykinin. These tissue hormones cause vasodilation. But what happens when the damaged or infected cells are not destroyed or eliminated? This is where the adaptive immune response comes to play. Thank you for watching.